So, welcome back to this class on hardware security. So, we shall be continuing our discussions on masking. So, in the last class we basically essentially defined how masking works, but in today's class we shall be trying to see how masking and glitches essentially work together in a sense, like how glitches can be applied to break masking. Okay. So, we shall be so let us continue our discussions on this topic. So, as we have seen in the last class, right, if we want to mask a nonlinear circuit like Z XOR XY, one potential way of masking is as shown here, and theoretically this should be secured against a first order attack. Okay. But we discussed, right, this is not even secured or not secure in against first order attacks if there are glitches. Okay. So, in order to understand that, right, we will try to take a little bit look into what essentially, so before I go into that, right, we will basically take a little bit of look into what are higher order DPA. Okay. So, in a higher order DPA, this is exactly like a first order DPA, where in a first order DPA, as we have seen, right, where we process on a single point on the power trace. In second order attacks, we exploit the joint leakages of two important or two intermediate values that are being processed by the device. Okay. So, basically it essentially means that if there is a power trace, and suppose, right, you are basically like this is your corresponding power trace, and in the previous case when you are doing a first order attack, you are basically targeting on one point on the power trace. Okay. But if you are doing a second order attack, then you are basically targeting 2 points on the power trace. Okay. It may happen that here you are processing F1 and here you are processing F2. Okay. So, now we will be considering the joint leakage of F1 and F2, and as we have seen, right, that if F1 and F2, right, together depends on all the shares of the inputs of the circuit, then essentially it will still leak the information about the actual data. Okay. So, therefore, right, we here exploit the joint leakage of two intermediate values that are processed by the device. The attack works in the same way as the first order attack, except that we pre-process the trace first. Okay. So, for example, right, if we know that the points in the trace where F1 and F2 are processed, then I would try to combine their leakages. Okay, and then, right, I will basically kind of pre-process the trace and create another pre-processed trace, and then I will be applying a first order DPA on that. Okay. So, what I will be doing is, suppose like I observe the power consumption here, and the power consumption here, right, at this point is say PT1, and the power consumption here is PT2, because these are two time instances T1 and T2. Okay. So, then I will basically combine, for example, this value like PT1 minus PT2 whole square. Okay. So, therefore, basically I will now replace these two power traces by a single point on another power trace, which is say PT. Okay. Which is essentially the nothing but the like the difference and then taken the square. You can of course replace it by some other function, but this is a very common pre-processing operation. Okay. And then once you have pre-processed this power trace, then you basically apply a normal first order DPA, as we have seen. Okay. So, like the normal correlation power attack, for example. Okay. So, therefore, the whole idea is that you are trying to kind of combine the leakage of 2 points. Okay. And that essentially, as we have seen, is that if it opens up the shares, then basically the countermeasure is not secured against such kind of attacks. Okay. So, therefore, right, I mean, so therefore, this brings us to a model which is essentially also used hand in hand with a dth order attack, which is called as probing model. Okay. And this is a very useful model to analyze what are glitches or the glitches inside the circuit. Okay. So, idea is that here the attacker can observe the values of up to d intermediate wires of the circuit per bit during the computation within a certain time. So, this is a more stronger form of adversary, where we are trying to kind of allow the attacker to observe the values of up to d intermediate wires. Okay. So, suppose you have got a circuit. So, remember, for example, the masked circuit, and I am allowing the attacker to observe, say, 2 intermediate wires or maybe 3 intermediate wires, depending upon like my notion or model of the adversary. Okay. So, in a general case, suppose the attacker can observe d intermediate wires of the circuit per bit during the computation within the certain time, and and this model or the d probing model is very much linked with what is called what we have seen is as the dth order DPA. Okay. And the similarity is because of the fact that the attack order in a higher order DPA corresponds to the number of wires that are probed inside the circuit per unmasked bit. Okay. So, because, right, when you are so the idea about a higher order DPA would be to basically kind of combine multiple leakage points, and in the probing model also you are trying to probe inside the circuit and you are basically observing the information of those observed points. Okay. So, you are allowing the attacker now to observe, say, d points inside the circuit. Okay. and this is essentially kind of similar to the higher order DPA, where essentially here and essentially has got a very close relation between them. So this relation or this result implies that if a circuit is secured against D probes, then combining D power consumption points will not reveal any information, and therefore, right, it should be secured against a dth order adversary. So if the operations, if the operations that correspond to the probed wires are in parallel, like suppose like if you are observing multiple points together and they are working all together, they are working simultaneously, then this is equivalent to the security notion that we have against dth order DPA. Okay, that means when you are doing a DPA with dth order statistical moment. Okay, like as we have seen in the second order attack, you do an attack with a second order statistical moment, okay, and not like the first order statistical moment, which we are usually doing in our normal first order DPA attacks. So note that this is a stronger form of model probably stronger than the higher order DPA. If a system is secured against deprobing attacks, then it should be also secured against the dth order DPA. Okay, and therefore, right, we will basically try to use this probing model to analyze the security of a given cipher. So the idea is that if you can ensure that your circuit is secured even when the adversary is able to observe D intermediate points, then that means, right, even if it combines D points in the power profile, then also, right, our system should be secure. Okay, so that is essentially the inherent idea. Okay. So now we will basically kind of analyze our masked gate. Okay, and we will see the masked gate and we will analyze the masked gate, allowing the observer to observe intermediate points. Okay. So what we will do is, in order to analyze this, so what we will try to do is basically we will try to kind of consider this truth table. Okay. So in the truth table you can see that this is essentially nothing but pretty much the masking that we have just now seen. Okay. So this is the masking that we have seen when we are considering the functions f2. Okay. So if you remember, right, this is the function that we have seen here, which is essentially z2 XOR x1 y2 and so XOR with x2 y1 XOR with x2 y2. So here we are basically trying to observe this particular circuit, but under the presence of glitches. Okay. So the probing model, actually is an important point to keep in mind. The probing model captures the effect of glitches by letting the attacker gather information on inputs like y1, y2 and also intermediate values like x2, y1, x2, y2, x2, y2, etc. Okay. So therefore the attacker is now able to kind of probe inside the wires and basically is able to see the internal wires. Okay. So now the idea is that if you are still secured, then that means that if you are combining the power leakages because of these intermediate results, you are still not able to do, or you should not be still able to do an attack. Okay. And therefore, right, this is a very strong attack model, and therefore, right, if we can show the vulnerability or the protection against this kind of attack models, then essentially our designs are very sound. Okay. So now the question is, right, why is this design kind of vulnerable against like in the presence of glitches at x2. Okay, and note that here I assume that the value of z2 XOR of x1 y2 essentially is shown over here, and this essentially can take values like 0 and 1. Okay. So basically I am kind of considering the inputs here, we are considering the inputs at this point, which is essentially nothing but z2 XOR of x1 y2. Okay. And the other parts essentially are shown here as x2 y1, okay, and x2 y2. Okay. So what we assume is, so if you want to read this table, the way to read this table is that you see the value here. Okay. So suppose the value is 1. Okay. So that means, right, we are basically assuming that there is a transition that y1 makes from 0. Okay. So all these circuits are, all these values are pre-charged to 0. And therefore, right, if I write y1 over here, that means I am considering this glitch. For example, I am considering this glitch which essentially makes this transition like this from 0 to 1. Okay. Likewise, if I write y2 is equal to 0, that means there is no transition because 0 remains a 0. If you consider x2, then that means again there is a transition from 0 to 1, which is shown over here. If I write z2 XOR x1 y2 is equal to 1, that means again there is a transition here as shown over here. Okay. So this point essentially makes a transition. So now there is an interesting difference between the transition of x2 and the transition of the remaining things, because in this circuit we assume that x2 comes little bit later, say delta time difference later compared to the other glitches. Okay. So that means, right, if I consider the glitch y1 and x2, then if y1 is coming here, then the x2 glitch comes a little later. So, it comes something like delta time difference later. Okay. So, therefore, right here if you consider that the output is an AND gate. Okay. So, therefore, the output is an AND gate. So, here 0 gets processed with so 0 0 the output is 0. So, therefore, the output becomes 1 only after delta time difference. Okay. So, therefore, this 1 becomes 1 after delta time difference. Okay. Whereas, this glitch is over here which is at the point 0 for example, and that would imply that since this glitch comes little later. So, therefore, the output of this XOR actually makes a transition like this. Okay. Because that we know that the two glitches, right, or the two input glitches are delta time difference apart, and therefore, there is a small time instance when both of these inputs become 1, and therefore, the circuit becomes 1 over here and the output becomes 1 over here, and then again comes back to the steady state 0. Okay. So, likewise, right, if you consider the glitch here, then this glitch is shown here. Now, here there is no transition, okay, and there is no transition because one of the inputs is held to 0. Okay. So, therefore, this transition, and if I combine this with no transition, then here also I get a transition like this. Okay. So, therefore, these transitions are at the instance delta, likewise this instance is at that instance delta. So, now if you consider the number of transitions before delta and at the time of delta for both the AND gates and the XOR are what are being shown here in this particular table. Okay. So, you can observe. So, let us see the AND first. Okay. So, the AND, right, essentially makes a transition at the instance of delta. This is the only transition which the AND gate is making. Okay. Here this AND gate is not making any transition. This AND gate is not in our account, but what we are considering is this AND and this AND. Okay. Out of which this AND gate never makes a transition, but this AND makes one transition at the time instance delta. Okay. So, therefore, we write here as 0 plus 1, which means like previously there was no transition, and at the time instance of delta there is one transition. Okay. If you observe the XORs, then you can see that before also there was one transition from 0 to 1, here also there was one transition from 0 to 1. So, there were two transitions, okay, that is 2, and after or at the time instance of delta there is again a 1 to 0 and a 1 to 0 transition. So, again there are two transitions. So, this is 2 plus 2. Okay. So, likewise you populate this entire table. Okay. And now observe the average power for the AND gate, okay, before the transition and after the transition. So, you will see here the average right here is 0 at the beginning and again 0 here, but after the transition, that means at the instance of delta, here the sum is 2 plus 2 which is 4, okay, which is essentially in the case when y is equal to 0, okay, which is the actual unmasked data. Likewise, if you process it for y equal to 1, then you will see that again this essentially is 0, whereas this sum is 1 plus 1 plus 1 plus 1 which is again 4. Okay. So, that means right if I add up these ones then I get 4, and that means right the average is dependent on 4 transitions and 4 transitions. So, therefore, the glitch power is not leaking any information. Okay. On the other hand, if you do this exercise for an XOR, you see that before the glitch there is no problem, because again you have got 2 plus 2 plus 2 plus 2 which is same as 2 plus 2 plus 2 plus 2 here in the case of y equal to 1. But for the case after the glitch, right, or after the transition, you will see that the sum here is 1 plus 1 which is 2, and here it is actually 1 plus 2 plus 1 plus 2 which is essentially 6. Okay. So, that means right you see that now there is a dependence, here it was 2 and here it is 6, right. So, the average power is varying, okay, and the average glitch power is varying and is also dependent upon your intermediate like your unmasked data. Okay. And that implies that there is an average power consumption because of the XOR, and the XORs are the reason or the culprit why this particular implementation or this particular masking is still vulnerable in the presence of glitches. Okay. Because note that when you are doing the attack, you need not like get into the circuit and try to count glitches actually. Okay. The idea is that the glitch power being correlated with the unmasked data, if you just do a power attack, right, albeit with much more observations, you still will be able to get the key. Okay. And therefore, right, I mean the whole point is that, or the reason why this attack is working is because of the fact that the glitch or the glitch power is correlated to the unmasked data. Okay. So, therefore, right, you would like to implement this in a way so that these kind of attacks do not work. Okay. And that is essentially what we will see subsequently on how to perform. So likewise, right, so therefore the overview on masking is as follows. So we have got where we have got an input mask, we are in a first order masking, we have got two input shares, that means the input, so we have got the mask. The idea is that there are two shares like S and S dash, or two parts which are processing. So there is one part which processes the mask, as I said, independently, which processes on the mask and gives you this output out1, and then the other part of the circuit, which is S dash, okay, which actually processes on the mask data, where the input is XORed with the mask, and it processes on that part of the data, and it gives you the out, okay, gives you the output. Okay. So note that if you combine out1 and out2, you should be able to get the out. Okay. So the idea here is that you also observe that S dash processes on the mask as well as on the input XORed with the mask, okay, and it gives you the out the result which is out2, okay, whereas the part which is S, right, processes only on the mask value. Okay. Likewise, if you want to perform a second order masking, as we have seen that this first order masking is vulnerable against a second order analysis. If you want to protect it, right, then you would basically now break up the circuit into three parts. Okay. So S, S dash and S double dash, where S and S dash both processes on the mask 1 and mask 2. So this processes on mask the first part of the mask, this processes on the second part of the mask, whereas S double dash processes on the input which is masked. The input now is basically masked with the two masks, mask 1 and mask 2. So therefore I get the corresponding masked result, and therefore this part processes not only this part of the input, but also which is the mask data, but also processes on the mask values like mask 1 and mask 2, and gives you the third shared. So now the idea is that if I combine these three output shares, I should get the corresponding result which is out. Okay. So of course, right, it has to be done in a much more careful manner, because as we have seen that although theoretically this is secured against first order attacks, but this is not secured in the presence of glitches. Okay. So again, let us take a look into, or take a closer look into this by considering just the traditional masking of the AND gate, which is the Trichina AND gate. Okay. So again, you can observe that here there is a leakage. So this is your traditional masking as we have already seen. Okay. But in the presence of glitches, this is still vulnerable against attacks, okay, as we have again seen, but let us try to redo it on the classical Trichina's gate. Okay. So here you observe that we consider inputs like, so basically we consider the fact that y is essentially the XOR of y hat, which is my masked y with the mask. So the mask here is B, or denoted as B. Okay. So again, so therefore y is nothing but the XOR of, or rather y hat is essentially the XOR of y and B. So y has been masked with B to give me y hat. Okay. So now if I observe this table, that means that would imply that if y is 0, then the masks are 0 0. If the y is 1, then it is 0 1 or 1 0. Likewise, if the y is 0, right, it can also be masked as 1 and 1. Okay. So now if you observe, right, what happens, right, in this circuit when we consider that there is a glitch in the input x hat. So x hat is the mask data corresponding to x. Okay. So this is very simple to observe that if I consider this glitch here, and suppose I fix the input here. So let us consider the last row in this table. Okay. So the last row in this table tells me that y hat is held at 1, and it tells me that b is also held at 1. Okay. So you see that I have held y hat as 1 and b as 1, and I am considering the glitch x hat. Okay. So I am considering that there is a glitch here x hat. Okay. So you can observe that if this is 1, then that would imply that this glitch will get propagated here. So I will have a glitch here in this way. Likewise, if there is a 1 here and a glitch here, then this glitch will be propagated here as shown here. And likewise, right here, if I do not consider any activity in this part of the circuit, then this glitch will also get propagated to the XOR. Okay. And this glitch will, and this glitch will both will get propagated here as shown here in this glitch. Okay. So now if you consider therefore the number of glitches in the AND circuit. So you will see that the AND circuit there are two glitches, this one glitch and this another glitch which is shown over here. Again the XOR, right, there are two glitches which are shown over here. So therefore we write here 2 and 2. Okay. So likewise you can try the other three cases, and you can see that this is the kind of annotation of the number of glitches for the AND and the XOR. Okay. Again, right, if you try to relate the glitches with the unmasked data. So in the unmasked data here is y. Okay. So, if you consider the cases, for example, like y equal to 0, like y equal to 0 is in this case and y equal to 0 is in this case, the AND gate, right, has got 0 toggles here and 2 toggles here. So, if I take the average, it is 0 plus 2 by 2. Okay. If you consider here, right, this is 1 plus 1, again the sum is 2. Okay, right. But if you do the same exercise for the XOR, you will see here it is 0 plus 2, but where it is here it is 2 plus 1, which is 3, again it is different. Okay. So, again you see that the number of glitches for the XORs are essentially getting correlated with your unmasked data, which is y. So, this again tells us that even the trichiness AND gate is also vulnerable to glitches. Okay. And therefore, right, this is not even secured against first order differential power attacks. Of course, right, I will require more observations, but still, right, the attack will work. And this essentially is important to understand, because like we will see as we will see subsequently, right, we will be using this fact and we will be keeping this fact in mind, right. We will basically try to construct a better design, which is essentially called as TI or threshold implementations. So, the idea of threshold implementations is based on multi-party computations and secret sharing. The idea is that TI of any function is used, and the basic objective is that if I take any function and I suitably apply a TI or threshold implementation, then it can be used as a dth order DPI countermeasure on the device that reveals a linear combination of the intermediate values noisy leakage. Okay. Of course, right, there are 4 important properties that a TI needs to satisfy, and I will be like one by one defining those criteria. They are called as correctness, uniform masking, non-completeness and uniform sharing of a function. Okay. So, we will try to see how these kind of properties are defined and how we develop on them one by one. So, to start with, right, what is the basic idea of a threshold implementation? So, suppose I have got a function which is fx equal to a, which basically kind of takes an n bit value and transforms it into another m bit data. So, the idea is that now we will split each variable x into Sx shares. Okay. So, like we were having d shares. So, suppose like I use Sx to indicate the number of shares that I use for my input data x. Okay. So, basically that means that if I take x, right, I basically split x into x1, x2 like this, right, to x Sx. So, there are Sx shares of x. Okay. So, that means if I XOR these things, right, I should get the original data. So, therefore, right, I mean with this like sharing. So, therefore, if I take an n bit input like x1 to xn, then basically it means that I break up x into x11. So, these are like my individual shares. Okay. So, x1 has been broken up into x11 so on till x1 Sx. Likewise, right, xn has been broken up into xn1 to xn Sx. Okay. And this you can indicate as now as a vector, say x1 to xn. Okay. So, this vector x1 to xn is basically therefore every element in this vector x1 is therefore having Sx shares. Okay. So, now what we want is that we would like that the function f, right, it will also be broken up into say s shares f1 to fs, okay, such that every function say f1 will now operate on these shares and will give me a vector a11. Okay. So, therefore, for example, f1, right, will give me a1. So, remember that it will also process on n bits, okay, and basically, right, give me a result which is a11 to am1. Okay. Likewise, the fs circuit or the fs part of the circuit will also give me an output which is a1s to ams. Okay. And now what you can observe is that you can now treat these things like a1 to as, right, as s shares, and I can indicate that as say the vector a1. Okay. So, therefore, right, I will have a1 to m such shares, and that gives me my vector a as shown over here. So, this is my vector output vector a. Okay. So, therefore, what we do is basically we take this mathcal x and mathcal a to indicate the vectors for the input and the vectors for the output, and the function f is also a vectorial function, because now it is a combination of s functions. Okay. So therefore, right, so therefore the idea is that f is implemented as a vector of functions as shown here as, so the vector f, which is a combination of f1 to fs, okay, and the whole idea is that each of these functions is therefore called as a component function, okay. So you can also like simplify this notation slightly by taking that, okay, now I will represent this x1. So this is x1 is my input, for example, this was my input right here, as we have seen here. I had my inputs x1 to xn. I can represent this entire input as by the variable x, okay. So I can represent this entire variable, this entire part by the variable x, and each of these shares like like x11 to xn1. So this is my first component that we had. I can represent that as x1, okay. So likewise I will have sx because there are sx shares, okay. So therefore my so now what I will consider, so therefore this essentially is my sharing of the input x, okay. So remember that each of these x's here are not 1 bit values but n bit values now, okay. So therefore, right, if I can kind of generalize this and say that, so likewise, right, the output also will be masked in a similar way. So therefore now I will have f1 to fs. Each of these data will now, as we have seen, was giving me like a11 to a1s, okay, and am1 to ams, okay. So you can also imagine that these, right, essentially like for these components, like suppose you are observing this component, say a11 to am1, you can observe these as like a1, for example, okay. So what I mean is that you can like consider this part and write that as say a1, and likewise, right, there are s shares, so you can write that as say like as, okay. So this is your sh share, okay. So therefore, right, what it means is that for all a's, like for a is your m bit value, okay, and suppose what you can write this input. So basically now this function f takes the input shares indicated as x or mathcal x, and this function gives you an output share, okay. So this output share is indicated as a or mathcal a, and this implies that like if I that a equal to sigma ai, that means if I add up these a1 to as, okay, that means I add up the output of each of these functions, okay, for all these input shares, then this should satisfy like I mean then, right, I should get the output a. That means, right, if x gets mapped into a, right, by the function f, then that means, right, for all the input shares that I have for x, right, which is essentially denoted as say x1 to sx, for example, okay, they should, if I apply now the vectorial function is suppose indicated as f mathcal, then I will get output shares like a1 to say a sa, for example, so such that if I combine them I get the original data a, okay. So that is essentially the basic idea behind thresholding. Of course, right, we have to see how to implement it so that we essentially get security against the power attack adversaries, okay. So we will basically define the properties that we need in order to obtain that, but we will take that up in the next class. Thank you.